So, welcome back everyone. It's time to open up a new chapter in the DB2 course. This is one of the occasions, of the many occasions actually, in which there is an interesting non-empty intersection between database technology and the implementation of languages, programming languages. For example, the study of interpreters and compilers. And if you know me, you know that this is one of the areas that is super interesting to me, the intersection of database technology and programming languages. And the topic that we are going to study in chapter 7, expression evaluation, is just about this super interesting intersection. So let's see what we can find there. Expression evaluation. This is a topic that is sometimes ignored when it comes to the study of database systems and query processing, for example, because the focus tends to be on the access to the tabular data or efficient indices or page organization or I/O and so on. But if you look at a particular class of queries, the effort that the system, that the CPU and the RDMS needs to invest into the evaluation of expressions, which can become quite complex, may easily match the time for I/O, table access, index access, and so on. And it's really worth the effort to study the efficient evaluation of expressions in database systems. And to do that, as is the direction of this course in general, we will study a particular probe query. And you see the probe query Q6 I've prepared on this slide. The focus would be on the 3 lines because they constitute rather complex expressions that are being evaluated in the course of this query. So it depends on the cardinality of table ternary, of course, but these expressions might be evaluated 1,000 times, a million of times, and any cycle that we can save while we are interpreting these expressions can actually be very beneficial. All right, so what will Q6 do? It will just iterate over all the rows of ternary, call those rows t, bind them to row variable t, then access the required fields in that row. And there is not too many fields that are actually required in this query. It's just the TA field here and the TC field, but these are used multiple times. Given these TA and TC values, these expressions compute scalar values, and that will be the focus of the upcoming discussion. Expressions that yield scalar return values, so integers, boolean, strings, all of the scalar data types that we've been talking about in this course. The focus is not on tabular subexpressions or subqueries. It's about scalar subexpressions for the next few videos. Okay. So once we've extracted the TA and TC field, it's about the evaluation of arithmetic operators, probably some Boolean operators or string comparisons, geometric operations. But in this case of Q6, it's just arithmetic operators. Once we've evaluated all these expressions, we are ready to construct one result row and emit this into the result. This is Q6. Okay, so let's look at the explain output for query Q6. Okay, so let's run an explain verbose on query Q6. And what you can see is a very simple plan. It's actually a one operator plan, a one operator from the viewpoint of the relational data model. We would just be using a sequential scan to scan all the rows of the ternary table. So regarding the table access, the relational data model itself, this is a super simple query. The complexity lies in the evaluation of the expressions. In this case, all of these expressions are in the select clause. They could as well be in the where clause, in the having clause. So it's about expression evaluation in general. And you can see that if you use the explain verbose command in PostgreSQL, that you can indeed see the internal representation or the output of the internal representation of the expressions inside PostgreSQL. You can see that explicit parentheses have been introduced to reflect operator priorities. Okay, So that would be multiplication is evaluated before subtraction. Okay. Then you can see that some explicit casting has been introduced. So this is explicit casting of the column value A to double precision value so that it fits the other operand of the subtraction, which will compute the power 10 to the power of C. Okay, and you can see that the system has analyzed the types of the involved operands and has introduced typecasts where that would be necessary. There's also some partial evaluation going on. So as you can see, we have this constant sub-expression, the logarithm of 2 here in this expression. And for each of these evaluations of this expression, the logarithm of 2 will be a constant value. The logarithm is a real function. It gets a constant argument. The result will be constant, and you see the result, the constant result, actually embedded here in the plan. So only a compile time, a planning time evaluation of the logarithm of 2. We placed the constant here and saved the evaluation effort for the probably millions of times for the different row bindings for t that we get and that asks us to evaluate these expressions. Okay, so already some preparatory work has been going on. All right, so explain gives us an insight into the internal representation of queries, but if you would have a closer look at the real internal representation of arithmetic expressions, then you would probably find something else. So let's have a look at possible internal representations of expressions inside such a system. So here's really where the interesting intersection between database technology and interpreter and compiler technology comes into play. So RDMSs will use internal representations of expressions that are just the same as they are used by, say, interpreters. We would, of course, build an abstract syntax tree of the expressions first. And here's the abstract syntax tree of the very first expression that is occurring in Q6, the multiplications that are then combined by subtraction. You have seen that expression before on the previous slides. As you can see, the abstract syntax tree already explicitly mirrors the operator priority so that the multiplications are performed before the subtraction at the very top, at the root of this expression tree is performed. Okay, so we could use this tree shape. We could use this tree shape form of the expression to evaluate the query, to write an interpreter that walks this tree representation. But what you would normally find in high performance optimized interpreters for expressions is some sort of linearized form, a linearized form of this tree-shaped expression. Okay, so we would probably find something that is closer to what we see here in the middle and in the right-hand side column on this slide. So we would be able to generate this linearized form of the expression representation from this tree-shaped form by performing a post-order traversal of this abstract syntax tree. So a post-order traversal of this tree would first lead us to this node accessing column A of row T, and the post-order traversal would lead us to the 3 then, which would lead us to the multiplication, which would lead us back to this node, the A access, which would lead us to the 2, which would lead us to the multiplication, which would finally lead us to the subtraction here. That would be the post-order traversal order of the operators of the nodes in this expression tree. And if you follow this particular order, then you will find the operations in this linearized program to be ordered in just this post order of nodes in the AST. So access A first, then the constant 3, then the multiplication, and so on and so on. And the subtraction here at the very bottom of the program represents the root of the expression tree. Such a linearized program is a nice, compact memory internal representation of an expression. It's a pointerless in the sense that we here in this tree-shaped expression, we will probably have pointers that connect these individual nodes with each other. Pointers mean pointer dereferencing, means random memory access when the CPU accesses this tree structure and tries to walk it and interpret it. We have the chance to have very compact memory representation of these linearized programs instead. So that would be very instruction and data cache friendly for the CPU because we can have a contiguous region of memory which holds just this this linearized program. Also, the implementation of jumps inside this program would be very straightforward. So this is also the identification of the next instruction would be very straightforward. In this program, we would just walk an instruction pointer from the top to the bottom of this particular program, where we would probably have to dereference pointers, node pointers, as I told you, in this tree-shaped representation. So this is something that you would very often find, and you will also find this in the internals of PostgreSQL. So what's happening here? We walk the program bottom to top, and we would start with a scan fetch sum instruction, which would access the fields of row T. And as you can see, we are advised to only access the A field in this particular case. For this sub-expression, the A field of row T would be sufficient. We would access row T, we would decode the wanted fields, it's only field A here. We would place it in some spot where the rest of the program can access the contents of field A in a defined fashion. And this is what's happening in the second instruction, where we just do that. We access the contents of field A with this instruction of the interpreter, with the scan var instruction. The result of this instruction would be placed in a particular slot, memory slot, where other instructions can obtain or access the result of the scan var A. And you can see the result of the scan var A is conveniently placed in the argument of the multiplication that we will have to perform in a second. The other argument of the multiplication is just the constant 3, and it would be just placed here, ready for consumption by the multiplication. You see that the multiplication is invoked by a generic function expression evaluation opcode. So this invokes the function. The first argument of this function expression strict would be invoked, and its arguments would be these two slots. All right. The strict is an indicator that we indeed need both arguments. In this case, the A and the 3, to perform the operation of this multiplication operator. You can imagine that there are other operators out there that are not strict, which can do their job already when only one of the arguments is available. Think of the Boolean conjunction, for example, which would be which we could evaluate in if there is only one of the Boolean arguments available to the conjunction, at least in some cases. All right, but multiplication is strict. Once we have found the multiplication result, we will place it in the argument slot of this subtraction here. Okay, the program goes on, and you know the drill already. We would access field A again. We would generate the constant 2. We would place them in the argument slots of the multiplication, which when performed will place its result in the argument slot of the subtraction, which is the last top level function call, if you will, in this expression. The result of this function call would be the result of the overload expression. All right, you see this quite clever argument placement discipline that is performed here by this particular interpreter. this is exactly what is happening inside PostgreSQL. We don't need special registers to save the intermediate results of sub-expressions. We would just place the result of these sub-expressions exactly where they are needed, only briefly later on when the evaluation of the program continues. Another alternative way to store the results of intermediate computations would be a stack discipline. So each of the operations in my interpreter would get the arguments for the operation from a stack, and they would push the result of their computation on top of the same stack. So the stack would be the means of communication of intermediate results between operations, not some argument slots. All right, as you can see, this would lead to this program, or a program of this form, which is also a linearized program read from top to bottom. And if you compare the sequence of operations in this program, it is also obtained by a post-order traversal of the expression tree here on the left. Okay, so this would be the access of the A field in the T row, and we would place the A field on the stack, which would now hold one element. We would push the 3 onto the stack, which would now hold 2 elements. And this is all we need to perform the binary multiplication operator, which would consume 2 arguments and then place one multiplication result on the stack, leading to a stack that contains only one multiplication result. And the computation would go on regarding the multiplication of TA with 2, and we would now have 2 intermediate results on the stack. Okay, this is all that the subtraction needs to perform its job. It would leave us with exactly 1 element on the stack. This is the final result of the expression. Okay, so this also is a very simple discipline, and this stack-based discipline is actually something that you will find in older interpreters. The one here in the middle is the one that you will find in modern implementations of interpreters, but this is just as well. If you have ever seen a stack-based language like PostgreSQL, for example, or Forth, then the entire design of the language, not only the expression evaluation, would be centered around a stack. So all of these could be possible representations of expressions inside the system. And as I told you, this middle one is the version that you would find in PostgreSQL. So let's have a brief look at how an interpreter might look like that interprets a program like the one that you've just seen in the middle column of the previous slide. In the middle column of the previous slide would show us a linearized program, and you will find this program shown again here with a bit more detail on the left in the program array. We would really have an array of instructions which would make up the program. All right. The current instruction to be performed would be pointed at by IP, by this pointer IP here, which is an abbreviation for instruction pointer. And of course, we expect the instruction pointer to walk down this program array as the program executes. But this would be the current instruction that we are looking at and that we would try to evaluate now. What exactly will this instruction ask us to do? Well, we can see it in the opcode, in the OPC equals 1 here, in the opcode field. This would be an indicator of what this instruction is indeed supposed to do. All right. We would use that offset 1 and perform a lookup in a different array, in the so-called dispatch array. In the dispatch array at offset 1, opcode 1, in the dispatch array, we would find a pointer to a routine, a pointer to a function inside our C implementation. In this case, it would be the scanvar function. And we would find the code that is part of the scanvar function. This would be just a simple representation of the code of the scanvar function, the function that accesses the value of one particular field in our rows. Okay, so let's have a look at what scanvar does for us. It, of course, accesses the wanted column. In our example, this has been the column A. So I'm not showing the details here, but we would access the column A value and would get the value of the A column in the current row. And we would place it where this IP res field points us to. So the IP res field, you can see that this is one of the fields of our opcode. This would be a pointer to the argument slot where the value of the A field should be placed for further processing. You have seen the argument slot idea on the previous slide. Okay, so because the scanvar function is really a very simple function, there's not much else to do. All that would be left to do is now to increment the instruction pointer. We have done our job. The next instruction is now the current instruction. So this is expressed by simply this simple increment. And the increment would lead the IP pointer to point to the next instruction here. All right. So where should that lead us? Well, we would just read the opcode of this new instruction. The opcode of that new instruction is 3. We would perform a lookup in the dispatch table regarding the offset 3. And this is exactly here. All right. And 3 would point us to this particular routine, to the const routine. Okay. So this would now be the routine to evaluate. And as you have probably noticed, the implementation of the scanvar instruction, of the scanvar opcode, has directly led us to the implementation of the next instruction in the program. All right, so that go to the last instruction of the scanvar opcode led us directly to the first statement of the next opcode implementation, of the const opcode implementation. This is called threaded interpretation. We will just thread the different opcodes, or the implementation of the different opcodes, directly together without any special interpreter, top-level loop or something. The implementation of one opcode would just directly invoke the implementation of the subsequent opcode. This is called threaded interpretation. Super efficient. All right. So this would be just the const opcode. So what it would do is just access the constant itself, the literal itself, which is actually embedded inside, embedded inside the opcode itself. It would just take this particular value and place it into the argument slot of the correct subsequent opcode. The correct argument slot is just pointed to by this res field again. Okay, so again, const would have done its job at this particular point, and it would be time for the threaded interpreter logic to just invoke the next the code for the next opcode in our program. All right, as you can see, this implementation of a threaded interpreter would rely on so-called computed gotos. So the address to which we have to jump here, the next opcode implementation that we have to invoke, is an address that is being computed by this lookup in the dispatch array. And this is a feature of implementation languages, in this case C, that is not widely found, but it's commonly found in languages that are considered rather low level. So jumping to a computed address is something that is very easily possible in C, and this is what a threaded interpreter makes use of. You will find exactly this idea implemented, really literally implemented inside PostgreSQL. So if we switch over to the PostgreSQL source code for a second, and if we look at the exact expression interpreter module of PostgreSQL, then we would find, for example, the dispatch table. The dispatch table is just the dispatch array on the slide that I've just shown you. This would be the dispatch table, and you can see the list of opcodes implemented by the expression interpreter of PostgreSQL. All right. This double ampersand symbol here would represent the address of the opcode implementation. So just the pointer that we were showing in the dispatch array on the slide that we've just discussed. And you can see that there are indeed some opcodes that we have already mentioned on the slide. For example, the scanvar opcode or the func expression strict opcode, for example. All of these are found indeed inside PostgreSQL. All right, so let's just let's just jump or look for the EEOP scanvar. All right, so this is the implementation of the scanvar opcode. A very simple implementation, just as simple as we've shown on the slide. As you can see, not much is going on here. Some internal lookups, and then, very important, the placement of the value of the accessed attribute, which is represented by @num here, not by an attribute name, but a number of the attribute in the considered row. We would just access this particular value and place it into the res or res value field, it's called here, in the argument slot of the consuming opcode directly. We would also leave the null status of this particular attribute there. So a bit more is going on here in the real Postgres implementation, as you probably have expected. And then everything is done. All that's left for us is to perform this EEO_next macro call. And this EEO_next macro call is the computed goto. I hope I can show you the implementation of the EEO_next. This is the implementation of the EEO_next. It would just increment the instruction pointer, IP on our slide, OP it's called in this actual implementation of PostgreSQL, and then we would call the EEO dispatch. All right, one more indirection, and the EEO dispatch is just a goto. It's just a goto to a computed address. Oh no, it's this one. I'm sorry about that. This would be the EEO. No, this is the dispatch. I'm sorry. So this is the real dispatch. This would lead us directly to the next opcode implementation in our expression evaluation program. It's just the computed goto. All right. So that would be the interpreted evaluation of expressions inside PostgreSQL. A very efficient interpreted, a threaded interpreter walking over the linearized form of the arithmetic and scalar expression that are embedded inside our queries. That's quite elegant and efficient already, but can still be a real runtime burden if the expressions become complex or if these expressions are evaluated many, many times. So in the upcoming video, we will look at alternative ways to interpret expressions inside PostgreSQL or database systems in general to gain just more speed for expression evaluation. Until then, have a good day and see you then.